Okay, so some problems from the review here. We're going to start with problem number 17. We're going to actually do the middle one first, then go back and do the first one, and then do the last one. So kind of a crazy order here. The idea in this one, the middle one, is that you can rewrite cotangent. Cotangent is the ratio of what two trigonometric functions? Cosine over sine. So when you divide by a fraction, the trick is to invert and multiply. So this is the same as the limit as x approaches pi over 2 of cosine of x, which is the numerator, times the reciprocal of this, which would be sine of x over cosine of x. And something nice and magical happens here, right? Cosine cancels itself out. So all you're left with is the limit as x approaches pi over 2 of the sine of x. At this point, the first thing you should be thinking about is the first thing you should always try, which is to plug in the limit. Now, that wouldn't have worked up here because you would have gotten a 0 in the denominator, but it works down here. What's sine of pi over 2? 1. Yay. And that's it for this first one. Now, same kind of idea with the first part of 17. That is, you're going to rewrite the fraction and invert and multiply. We're going to get some cancellation. Cosine terms cancel out. And then what you're left with is this. The limit as x approaches 0 of sine of x over x. Now, this late in the semester, you may not remember it, but this is one of a few given limits. These are limits that I said, okay, if you run across this, you just put down the answer. What's the limit as x approaches 0 of sine x over x? 1. And that's it. This is not something that you have to prove. Okay, in Calc 2, you'll learn a different way to work that one. But for now, that limit is just 1, and you can run with it. All right, so keeping in mind that sometimes we have defined limits that we know, let's turn our attention to the last of these problems in problem 17. And notice that I've got a common, or excuse me, not a common factor, but a constant of 5/3. I'm going to factor that out in front. Limit as x approaches 0 of 1 plus x to the 1 over x power. This is a good Calc 2 problem, but for purposes of this class, you were given this limit, and that limit is e. So it's just 5/3 times e. Yeah. Oh, don't. Yeah. So a couple of you seemed like you were working pretty hard on that one. Yeah, all you had to do is factor out the constant. So let me turn our attention next to problem number 18a. And this one has appeared in a couple places. We've seen it in one of our early exams, and here it is again in this one. The point of this problem is to recognize what the outside and the inside function are. So in the first instance, this can be written as cosine of x cubed. And it's just really asking you, do you understand that notation? On the other hand, this is sine of x to the 6. And I put in the parentheses there just to kind of emphasize what the outside function is and what the inside function is. You have to use a chain rule. And that's really what this is asking you, is do you understand the chain rule? So the derivative of the outside here is going to be 3 cosine of x squared times the derivative of the inside. What's the derivative of the inside? Negative sign. Good. Remember, if it's a trig function that starts with a c, it gets a negative when you differentiate it. Negative sign. How about the second one? What's the outside function there? Sine. So the derivative of sine is just cosine times the derivative of the inside. Derivative of the inside? Thank you. 6x to the 5th. And that's it. Now you can clean this up. You can bring the negative out front. Negative 3 cosine. I'm going to revert back to more of the standard notation. Cosine squared of x, sine of x, plus 6x to the 5th cosine of x to the 6th. So there you go. Again, what I want to emphasize is that what you need to know is the difference between the outside and the inside functions, which one's which in problems like that. Are we okay with problem number 18 there? All right. I think there was a request for problem number 19, even though you guys eventually figured it out. But it's worth looking at, because I asked you to use logarithmic differentiation on this one. So what's logarithmic differentiation? Well, it kind of combines differentiation with implicit differentiation a little bit. But the idea is this. If I start by taking the ln of this, ln on both sides, I can use the properties of the log to kind of split things up a little bit and make my life easier as far as differentiating is concerned. So on the right-hand side, I can rewrite this a little bit using the properties of logs. It's going to be the log of the numerator minus a log of the denominator. Now I'm going to rewrite square root of 3x minus 2 is 3x minus 2 to the 1/2 minus the ln of x minus 1 to the 5th. And now I'm going to use some of my rules for logarithms yet again. And let's kind of speed this up a little bit. I'm going to break this up into the log of x squared plus the log of 3x minus 2 to the 1/2. And those exponents are going to come out in front. So it's 2 ln of x plus 1/2 ln of 3x minus 2 minus 5 ln of x minus 1. Now the point here is that I've exhausted all my properties of logs. And I've got this as simplified as I can using the properties of logs. But remember, my ultimate goal here was to find the derivative, was to find dy by dx. I haven't done any differentiation yet at all. So let's work on the differentiation part. And let me do this here. Let's put a little green box around the y, because we're going to differentiate with respect to x. And when we differentiate both sides with respect to x, d by dx, then, well, when you differentiate a log, you get 1 over that term, but it's not enough just to put 1 over y. What else do I need? dy by dx. dy by dx. Now on the right-hand side, since we're differentiating with respect to x, and I've got x's here, I don't have to apply the chain rule like I did on the left-hand side. I'll get 2 times 1 over x plus 1/2 times 1 over 3x minus 2, but I'm not done here. What else do I need here? 1 over u times the derivative of u. What's the derivative of that? Times 3. So I've got to apply the chain rule there. And how about the last term? What's the derivative of that last term? Good. 5 times 1 over x minus 1. Now let's clean this up a little bit. I want to get dy by dx all by itself. And I've got this 1 over y term here. So what I can do is replace that, or say, I should not replace that. How about if I multiply both sides by y? If I do that, on the left-hand side, those y's are going to cancel each other out. I get dy by dx equals 2 over x plus 3 over 2 times 3x minus 2 minus 5 over x minus 1 times y. But let's save ourselves a little bit of writing here. Instead of writing this all over again and putting a y here and then replacing it, let's just put in what y represents. Y was initially defined as this function. So it's times x squared square root of 3x minus 2 over x minus 1 to the 5th. Now, I'm not sure if on the final exam I would tell you outright to use to use logarithmic differentiation or not. But if you have a case where you can simplify an expression using logarithms, then maybe you want to use it. Okay, it doesn't have to be just for the problems that I tell you. The only thing you have to worry about is being careful not to use properties of logs that don't exist. I see that happen quite often, that people do something like this. ln of a plus b equals the ln of a plus the ln of b. Well, no, it doesn't. If you're not confident in your properties of logs, then maybe go back and get some help with that. How are we on problem number 19? Okay, onward. Problem number 41. Okay. The infamous isosceles triangle, inscribed in a circle of radius 8. So, if this circle has a radius of 8, then these lines drawn from the center to the vertices of this triangle also have a distance of 8. And what we want to do is we want to try and figure out excuse me, the dimensions of a triangle that have the maximum area yet fit in this circle. Okay, so one of the things I'm going to need is to figure out a formula that tells me the area of this triangle. So, all right, let's think about that. So here's my picture. I need to label a little bit more here. Can you tell me what the length of this side is going to be? Square root of 64 minus h squared, right? Okay. So that's just the length of this side. Remember that across the base I've got that side twice. There's 4 basic steps in these things, the way I've covered them. Picture, function. We need to come up with a function that tells me the area of this triangle depending on how far down I take my cut. So let's see. Area of a triangle is 1/2 base times height. So 1/2 base times the height. Well, the height is going to be 8 plus h. How about the base? Perfect. 2 times square root of 64 minus h squared. Now the 2's cancel themselves out, and I can write a of h is 64 minus h squared to the 1/2 times 8 plus h. Nice. So I have my function, and it depends on one variable. It depends on h. One important thing that you need to keep in mind about this is 8 can't just take on any value. There's only certain values of h that'll make sense. What's the limit for h? Yeah, it can't be any bigger than 8, right? Because if I make h closer and closer to 8, this triangle is going to get smaller and smaller and skinnier, even though it gets taller. And eventually, at h equal 8, then you're going to have a straight line. You're not going to have any width left to your triangle. So our interval is 0 to 8. Picture, function, interval. What comes next? The analysis. Good. So what we need to do next is to differentiate. So let me rewrite this problem a little bit, and let's work on the derivative. Now the derivative's a little bit of a pain here. You're going to need to use the product rule. So we've got F and a G. So we got F and G. Let me just clean this up a little bit. There, it's a little better. So let's try and find F prime. F prime is going to be 1/2 times 64 minus h squared to the negative 1/2. That's the derivative of the outside, but then I also need to differentiate the inside. Negative 2h. Good, so let's distribute that, and I'll get negative h times 64 minus h squared to the negative 1/2. G prime is going to be a little bit easier, isn't it? What's G prime going to equal? 1. So that's nice. So I need A prime of h is going to be F prime G plus G prime F. So F prime is going to be negative h, 64 minus h squared to the negative 1/2 times G, which is 8 plus h, plus G prime, good, times F, which is 64 minus h squared to the 1/2. Now, part of why I like these problems, it's something that we've practiced a lot, is working with these negative exponents. The challenges you're going to face is we have to eventually factor this and figure out where this is equal to 0 or where it does not exist. And I think it's really where it's going to equal 0 is going to be the heart of our solution. So you look at these exponents and you factor out the smallest exponent. Yeah, so we're going to factor out 64 minus h squared to the minus 1/2. So 64 minus h squared to the minus 1/2. Now I'm going to show all the gory details so that if you're watching this at home or someplace else, that you can kind of follow along. You don't necessarily have to show all of this on an exam. Maybe you can do some of it in your head. So 64 minus h squared. When you factor something out, you're really dividing each of those terms by that factor. So 64 minus h squared to the 1/2, 64 minus h squared to the negative 1/2. So all I've done here is I've taken this and I've divided each of those terms by that thing that I'm factoring out. Okay, so some nice cancellation here. Those terms cancel out completely. So what am I left with? I'm left with 64 minus h squared to the negative 1/2, and then negative h times 8 plus h. And what happens over here with those terms? Yeah, it becomes to the first power because you're going to subtract the exponents. 1 minus negative 1/2 gives me positive 1/2. So 64 minus h squared to the first power. Okay, so let's clean this up and see what we can come up with. 64 minus h squared to the minus 1/2. Let's see. Distribute that. That's going to be minus h squared minus 8h plus 64 minus h squared again. And there's like terms that I can collect. So when I collect like terms, I get minus 2h squared minus 8h plus 64. And finally, we're getting this thing closer to something that I can deal with. I'm going to bring this term down into the denominator and Do you see anything I can do in the numerator? All right, so let's factor out a negative 2. That's going to leave behind h squared plus 4h minus 32 over 64 minus h squared to the 1/2 power. Now, as a reminder, the critical points are places where the derivative is 0 or doesn't exist. Now, this wouldn't exist if h is negative 8 or 8. But neither of those points are in our interval, right? Our interval is 0 to 8 with parentheses. So we don't have to worry about those. So we don't have to worry about where the denominator is 0 at all. We do have to worry about where the numerator is 0. So where does 0 equal negative 2 times h squared plus 4h minus 32? Nice. So you can factor this. It'd be really mean if I gave you a problem this long that didn't factor, right? If you had to pull out the quadratic formula. Man, I can see the backlash on social media already. Yeah. All right, so this one factors pretty nicely. You get two possible solutions, negative 8 and 4. Obviously, negative 8 is not in our interval. 4 is in our interval. I'm thinking that most of us probably wouldn't want to deal with the second derivative here. That'd be a real pain. So we could work with the first derivative, and I'll let you kind of verify this later. A of h, a prime of h, so at 4. So at 4 we had a derivative of 0. And if you test a point, say, to the left of 4, something like h equal 1, if I put a 1 here, the numerator is going to be positive, and so is the denominator. If I put in something a little bit bigger than 4, say like a 5, then the derivative is negative. Why am I concerned about that? What's this telling me? Yes, exactly. The function is increasing, then decreasing, so this point has to be a maximum. Yay. So now on some of your tests this semester, when you've gone that extra step and show me that, I've given people extra credit. It's not something you count on, but it is something that you might want to be on the lookout for. Any other thoughts on problem number 41 here? Cool. Let's call it a day here.